Hello students, in this video we'll show that the Bessel function of order 0, j0 of x, has an infinite number of zeros or roots. Recall that j0 of x, which is the sum, and goes from 0 to infinity, of negative 1 to the n, over n factorial squared, x over 2 to the 2n, solves x, y double prime, plus y prime plus xy equals 0, right? And of course, I can preserve the structure of the singularity by writing this as y double prime plus 1 over x y prime plus y is equal to 0. And what I'd like to do is I'd like to put this equation into normal form, right? So how do we put this equation into normal form? So recall what we do to do normal form. We take the coefficient p of x and we exponentiate that function. We exponentiate the integral of p of x over 2 to find out what the normal form is, right? So now my normal form, so now what we're going to do is we're going to let our solution, we let j0 of x be equal to m times v, right? Where what is m? Where m is e to the negative integral of p of x over 2 dx, and that's going to be our normal form. So what is this going to be? This is going to be e to the negative 1/2, and that's going to be just the log of x. So our integrating factor here is just x to the negative 1/2 power, okay? So j0 of x, which is 1 over the square root of x times v, satisfies this equation, satisfies, you can just plug this in and check, satisfies v double prime plus 1 over 4x squared v is equal to 0. Because remember, the whole idea behind normal form is that normal form, the equation for v will have no v prime term. And so if you do the calculation, you'll see that this is exactly the equation that v double prime will satisfy, right? So it's a good exercise to do that. So plug it in. This, of course, is just normal form. Normal form. Okay, because our q of x is equal to 1, so this, of course, is q. Then I have derivatives of p over 2 and then p squared over 4. So we can see that each of those things, the derivative of this, the derivative of 1 over x squared is negative 1 over x squared, and then p squared is also the form 1 over x squared. So the other coefficient over here, the terms that is p prime and then the p squared, each looks like in 1 over x squared, and so the actual number is just 1 over 4. Just do the calculation, figure it out. Normal form. And so now here's the beautiful thing. So that tells me that if I look at this function x, j0 of x, which is v, then I know that v of x will vanish when the function j0 of x vanishes. So v of x, so j0 has a root, j0 has a root if and only if v has a root. Okay? But let's be a little bit more precise about that, right? So let's be a little bit more clear about what I mean by that. What I mean by this is I mean that j0 of lambda is equal to 0 if and only if v of lambda is equal to 0. So in other words, the roots of v are exactly the roots of j0. Okay, so I'm going to try to classify the roots of this function v over here. So what I'm going to do is I'm going to use the following identity. And the identity says that if I have f times g double prime minus g times f double prime, what this is d by dx of f g prime minus g f prime. Let's check. If I do the derivative of this first one over here, I'll have an f g double prime. That's what I have over here. Then I'll have an f prime g prime. If I do the derivative of this term over here, I'll have a negative f prime g prime, then a negative g f prime prime. So that works. Great. And so now what I'm going to do is I'm going to let my f be v and my g be sine. So let f be v and let g be sine of x. Okay? That's for that particular choice what we have. Well, what we'll have over here is we'll have f, which is going to be my v, and then I'm going to have g double prime. Well, the second derivative of sign is negative sign, so that's going to be a negative g. So that's going to be a v times negative g, and then a negative g times f double prime. So what's v double prime? So v double prime is the negative, so it's going to turn into a positive. So negative is a positive v, and then a 1 plus 1 over 4x squared. So of course the v times g is going to cancel here and cancel here. And so the left-hand side is exactly just equal to v of x times g of x, which is sine of x over what? Over 4x squared. And this is equal to d by dx of what? Of f, which is v times g prime minus g, which is sine of course, times v prime. Okay, great. And so now what are we going to do? So now I'm just going to integrate both sides. So now I'm going to take this relationship over here. I'm going to integrate it over a particular interval. What I'm going to do is I'm going to integrate this. So let's consider the integral from 2n pi to 2n pi plus pi. Okay? So that of our function v of x times sine of x, which is our g, over 4x squared dx. Well, this is the integral of this derivative, so this is just going to be what? This is just going to be v times v of x times g prime. And what's g prime? G prime is just going to be cosine, right? Cosine of x. And then minus g, which is sine of x, times v prime. And this is evaluated from 2n pi to 2n pi plus pi. Now, of course, the sine at any integer multiple of pi is going to be 0, so those terms over there are gone when I plug in the limits. And the cosine, when I first plug in cosine, the cosine of 2n pi is periodic over here, so these terms are irrelevant. There's going to be the cosine of pi, which is -1. So this is, and the bottom one is going to be a cosine of 1, so they're both going to be negative. So both these terms are negative, and they're negative what? They're negative what? V of 2n pi plus pi. And then plus, because it's the same parity, of just 2n pi, whatever those numbers happen to be. Okay. So now let's think about this. So let's suppose that v of x is strictly greater than 0. In other words, it does not cross. It's always above the x-axis on the interval 2n pi to 2n pi plus pi. It's always greater than or equal to 0, okay? Then this term would be what? This would be positive. The sign between 2n pi and 2n pi plus pi is greater than 0 because it's basically just a shifting of 0 to pi. So on 0 to pi, the sign is above the x-axis. So this is positive, and this is positive, and this is positive. So the integral over here is what? This integral over here, under the assumption that v of x is positive, if v of x is always above the x-axis, it does not cross the x-axis on this interval, then this left-hand side is positive, then this would be positive, and this would be positive. This whole thing is negative. So if v of x was always positive, I'll have a positive is equal to negative. That's impossible. Likewise, what happens if v of x was always less than 0? So if v of x was always less than 0, what would happen? So suppose that v of x was always less than 0 on the same interval over here. Then what would happen? Well, then v of x would be what? Then I'd have a negative, a positive, and a positive. So then this whole thing would be negative. And if it was always negative, this would be negative, and this would be negative. So I'd have a negative and negative of a negative, that'd be a positive. So in that case, I'd have a negative is equal to a positive. That's impossible, which means that I cannot have strict positive or strict negative, which means that v has to cross the axis somewhere, right? Hence, v crosses the x-axis somewhere on the interval 2n pi to 2n pi plus pi for every n. So, okay? So I've just shown for every n, this function v has to cross the axis on that interval over here. So in other words, if I look at a particular value of n, so I plug in like n equals 2, for example, this would be here's 4 pi, and here's 5 pi, and then here's 5 pi, because I shifted over. That function v has to cross somewhere over here. I don't know exactly where it crosses, but it crosses somewhere over there. If I plug in n equals 6, between 6 pi and 7 pi, so between 6 pi and 7 pi, there's 6 pi and there's 7 pi, it has to cross somewhere over there. And I don't know if it's above or below, but it has to do either this or it has to do this, okay? So it has to touch the axis on that interval. And maybe it actually bounces off the interval. I don't know exactly how it does it. You can actually show the zeros are simple because it turns out the zeros of the Bessel function are related to the zeros of the Bessel function of order 1. So you can show they're actually simple zeros. So in other words, I've just shown for every interval of this form, for all n, v crosses the axis somewhere in that region. If v crosses, that means that v of that point is 0, which means that j0 is 0. So the conclusion is that j0 is an infinite number of zeros. So hence, j0 has an infinite number of roots. Thank you very much.